Alright, so atomic mass units. Now, if we go back to this in the periodic table, and for every box is an element, I'm just going to do this, and it's going to go 1.008. This is for hydrogen, correct? Alright, we have our atomic number, which we should know what that means by now. We got our symbol. And this is the AMU, or we could call it the average atomic mass unit. And the atomic mass unit is a unit that is derived from something else. Now, 1 AMU is equal to 1/12 the mass, and I know we talked about this yesterday, of carbon 12. So scientists took carbon 12 because carbon 12 was something nice and easy to work with, and they divided it into 12 parts, and they said one part of this is going to be called an atomic mass unit. And now we can compare all the elements with their atomic mass units to each other because we're all working on the same thing. It's like creating a meter or a yard or a foot. We have a standard way of measuring things now. Otherwise, we really didn't have something like that. So we needed to create a standard way of doing it. Now, the problem is, when you have elements that have all these different isotopes to them, they take up chunks of the element itself. And in order to calculate this, so to calculate an element's atomic mass unit, we need to know how much each isotope will contribute to the element's AMU. Now, in order to do this, we're going to do an example. And our example is going to be for element X. And we don't know what element X is. So it's an unknown element. And believe it or not, on the periodic table, there's no element called element X. Now, element X has two isotopes. So it has two isotopes. You could call it X6 or put the 6 up top with X, and 7X or X7. Now, we need to use both of these because element X is going to be made up of part of the first isotope and made up of a part of the second isotope. And we need to put both of those together in order to calculate that AMU for element X. Yeah. I know. I'm making a video. Now, with element X, I think the easiest way to do this is to well, that says isotope. You're going to put your two isotopes here, or Now, the second column is going to be mass, and that's going to be an AMU. It's mass in AMUs. And then we have a word called abundance. And then we're going to come up with something finally called our contribution. And you can do this, and for each one, you can create your table like this. Now, for this element, the mass in element, or for isotope X6, is going to be 6.015 AMUs. And now we're just dealing in AMUs with this. For X7, it's 7.016 AMUs. Now, I'll let you guys catch up on that for a second. For abundance, which is a big part of this, for abundance, this is going to be how much in a percentage. So this is going to be in a percent. How much does this take up out of the whole thing? We're going to say that this takes up 7.5% of element X. And the other one takes up 92.5% of element X. So if you want to think of like a pie chart, if this is all of element X, this chunk right here is your 7.5%, which represents the isotope X6. This part right here is 92.5%. It's not drawn exactly to scale. And that's for element or isotope X7. Now, creating the table, I think, is a whole lot more than just using the formula. Or a lot easier. Now, let me ask you this. In mathematics, can we use a percentage when we're doing our math, or do we have to convert it? We have to convert it. So we have to change this to a decimal. 7.5 becomes 0.075. 92.5 becomes 0.925. And in order to calculate the contribution of AMUs, so this is going to be in AMUs as well. To calculate the contribution of AMUs, we're going to have to first multiply these two together. And that's going to be our contribution. So we need to take our calculator. And I haven't hooked up my calculators yet, but we'll have them hooked up in a few minutes, they'll be hooked up 5th hour. You're going to take the 6.015 and then times 0.075, because we can't work with percentages. And in this case, it's going to be 0.451125 AMUs. So the contribution that the isotope X6 is going to contribute to the overall picture is only 0.451125 AMUs. And hopefully that makes sense, because it's only 7%. It's not a whole lot as far as percentages go. Now, for the second one, we type in the 7.016, multiply that by the 0.925, so it's 92.5%, and that's going to give us 6.4898 AMUs. So 92% is element 7. That's going to give us the most of it. Add them together. So I'm going to take this number and add on the 0.451125. And now I got a number 6.940925. Now I'm not going to use that. We're going to use significant figures here. We're not going to look at percentage for significant figures, because that's just a given type of number. It's a solid number that stays there. It has nothing to do with measurement. But this does. This says that our measurement was able to go to how many significant figures? Think back, because I know we haven't had a formal lesson on significant figures, but what's your best guess on how many significant digits? How many of these digits? Well, first off, how many digits are there? There's 1, 2, 3, 4. How many of them do you think are important? 1, 2, 3, or 4? All of them. In this case, all of them are significant. So we want to go to how many digits in our answer? We want to go to 4 places. So I know it's going to be 6.94. That's the first 3, but I got a 0 and then I got a 9 next to it. So is that going to make the 0 1 or is it going to keep it at 0? All right, it's going to round it up to 1. So element X, we just calculated. X has 6.941 AMUs. Now, after this, go to the periodic table. And find an atomic mass of 6.941. 941? Yeah. I added these two together. Okay. So, add the column. Because it's going to add the first isotope and the second isotope and the third isotope. If there's 3 or 4 of them, we add all 4 of them together. So, go to your periodic table, which is either in the back cover or it's on page 156 to 157. What was that?
How do you get that abundance?
It's going to be given to you. A lot of this information is going to be given to you because we just can't make it up. We just can't make it up. This certain element has to have the isotopes in certain abundances, and the isotopes themselves have certain atomic masses. So all that information is going to be given to you. You need to know how to put them in the pot the right way, make them up, and come out with the correct recipe. And that's what we're doing, is we're creating the correct recipe. So yes, sir.
So all we're doing is just multiplying and adding columns together?
You multiply those two, and then you get your answer, and then you add that column together to get your AMUs. So now we got to find which one has an AMU of 6.941. Oh, you have another question? Okay, you're right. It is lithium. But what's your question? It's going to be this is going to be given to you, and this is going to be given to you. That's how you convert a percentage to decimals. Right. So, like 100% is 1.0, and then you have to convert it to this because we can't use 100% in an equation. We don't do that. Now, this tells me that X is lithium. Because lithium has an atomic mass unit of 6.941. These are numbers we just can't make up and go with. Now, the equation looks like this. It would be whatever the mass for the first isotope is times its abundance plus isotope number 2's AMU times its abundance plus forever and forever and forever. If there's 6 of them, you got to do it 6 times. If there's 10 of them, you got to do it 10 times. Another way to write this, which is kind of what I wanted to show you, because we didn't get to this yesterday. We did it really quickly, but not that. I wanted to make sure that we understand what we're doing. Is this symbology. Now, chances are we're not going to use it, but since I got that math background, I like to throw this math stuff in at you. This, anybody know what this symbol is? It's a letter. It's not Z. It's Greek, so it's going to have a Greek name. Sigma. This is a sigma. And what sigma means in math is summation. Now, what operation do you think is summation? Adding. So this is going to be add whatever is defined. After the sigma. So it's the isotope AMU times its abundance. And this says add them all up. And so that's what we're going to end up doing. We're going to have to add them all up when we get to that. Now, I'm not going to break your backs and make you add up like 17 different isotopes and all that stuff. But you got to know the process and how we set this up. I think the best way to do it is from its table, where you set up the isotopes, and because it's all nice and neat. Then you put the AMUs in one column, you put the percentages in one column, you multiply them, and you get an answer. Multiply them, get an answer. Multiply them, get an answer. Add up all the answers, then you're going to get your AMUs for your element. That, I think, is the easiest way to do it. It organizes all the data. You can take a look at it, and you can say, all right, this isotope has this mass and this abundance, where sometimes in here it becomes a little bit confusing what you're talking about. And this is what you want to do, and this is what I want you to do. I want you to make things perfectly clear, because the clearer that we can make this stuff on our papers and then during our work and during everything that we do, the clearer it is, the easier it's going to be. You guys might want to resist that right now, but I'm telling you, I'm a pro at this. I've done things the hard way, and I've done things the easy way. If you do things the easy way, your life is going to be a whole lot easier. Shocker, I know. So this is an easy way to get this done. This is an easy way to get that done.